Welcome everyone to the second session of IT Superior Physics Talk. Today's speaker is Atiqur Rahman. He's a graduate student, physics PhD student at the University of Cape Town, South Africa. The title for the talk is Using Pulsars to Detect Gravitational Waves.
Hello. আমি স্লট নিয়ে নিলাম। তো সামি আমাকে বলছে যে it has to be in English because I ASTS. So okay. I'm Atiqur Rahman. I'm doing my PhD at the Applied Math Department at the University of Cape Town, and I am trying to work on pulsar timing array, which is the full form of PTA. And using PTS, we are trying to detect a certain polarization mode of gravitational wave. But in this talk, I will not go into such detail. I will just talk about how scientists are trying to detect the gravitational wave using the pulsar timing arrays. Here are the things I want to go through. One is what are pulsars? Number two is what is the gravitational wave, or how do we know that they exist, at least theoretically, and what is this pulsar timing array, and finally what are Hellings and Downs curve. So here is how the story begins. The story starts from a PhD student a long time back, and the student's name is Jocelyn Bell, and she was working on a telescope. And let me just show you the telescope first. This is a certain kind of telescope, and these are called radio telescopes. So what it does is it tries to catch the radio signals from some source. So what are the radio signals basically? They are basically change in voltages. And you need to amplify the voltage because it's very low. And what this kind of telescope used to do in the beginning of radio telescopes, it catches the signal and it writes on a plotting paper by hand kind of situation. So it's the electrical pen, it just goes up and down throughout a time series. So when Jocelyn Bell was trying to observe this telescope data and trying to make sense of it, she came across this thing one day. So you can see that there is this interference. You can see, is my cursor anywhere there? No, not yet. And at the middle of this plot, you can see it's written CP1919. And at the just over the 6th August 1967, you can see that it's written 1910, 1920, 1930. These are basically sky locations. So she started seeing this pattern every day, that CP9 1919. So what she did is she took out one day worth of plotting paper, and there she saw this periodic bump, downward bump, I would say, in this plot. And then she discussed it with her supervisor, and then they thought that this must be a signal from the outer space. Thus, they started calling it the little green man. They thought it was a signal given from the aliens. But then there's other pulsars started to come to notice, and people started to find out these things. You can see that I wrote that the first pulsar that they detected, it has a period of 1.3 seconds. So every pulse used to come at a 1.3 second interval. And they calculated the density. I mean, if they thought that it is coming from some external source, the source must have a density of 10 to the power 8 gram per centimeter cube, which at that time people used to know about white dwarfs. and it used to match with that. So they thought maybe it's coming from a white dwarf. After the second thought, the first thought was, of course, the little green man. And then what happened is, immediately after, they found another such signal that was giving like 0.033 second periods, that was coming at like very, very fast. And if you calculate the density of such object, it is very, very high. And it is higher than any white dwarf at the time. And that kind of density cannot be supported by electron degeneracy pressure. This must be something new. So scientists started to think that what is the signal now? And how can we describe it mathematically or theoretically? So they came up with this idea that there must be something like this, which we right now call pulsars. Pulsars are basically one kind of neutron star where you cannot, you no more able to uh, hold the electron degeneracy pressure. And I mean, how can I describe this? So in any star, there's two opposite forces work, right? One is the gravitational force, which tries to push it to its core, and the other is the degeneration pressure that pushes outward. And when these two stays in equilibrium, they sustain, and we get the light from it. But at some point, the electron degeneracy pressure fails to protect it from the inward force. And when it happens, the star collapses. And if the core mass is like around 1.4, which is the first child radius or something like that, 1.4 first child mass, I guess, to 3 solar masses, it is surely will collapse to a new pulsar. And a few other properties of pulsar is like it has very strong magnetic field. It has jets along the two magnetic poles, and most importantly, they are not aligned most of the time with its spin axis. What I mean by that is, in this figure, you can see that there's a neutron star at the center of this cylinder, and the rotation axis is this. So it rotates like this. And there's a magnetic axis which is not aligned with this axis but slightly tilted. And when it rotates around its axis, the magnetic axis cuts out a cone. And whenever the cone passes through the Earth sees one pulse at a certain time. And as to come across this cone, it takes a certain time. It just gives a consistent pulse period, if that makes any sense. Any questions till this point? Yes.
ভাই বেসিক্যালি হচ্ছে এখানে পালসার সম্পর্কে পড়ার সময় আমি জাস্ট একটু সার্চ করলাম যে রেডিয়াসটা কত বড় হবে, কারণ এটা দেখতে অনেক ছোট লাগতেছে। তাহলে হচ্ছে এটাকে স্টার কেন বলা হইতেছে? কারণ এটা তো অনেক ছোট, রেডিয়াসটা সম্ভবত 10^45 হতে পারে।
So basically it was a star, now it collapsed to a smaller region, right? So when it collapses and starts showing this kind of behavior, then we call it a pulsar only. And in this star there is only neutrons, there is nothing else. So all the electrons and all the positrons come together and creates a neutron. That is why there is no electron degeneracy pressure anymore. Now it can collapse to its core. So all the neutrons are like highly dense, and that is why its radius becomes shrinks to around 10 to 25 kilometers. So it is smaller than a town, but it is highly dense. Let's say the whole sun sits at Boira Khulna. So that will be the radius, and I mean the whole sun sits between Gollamari and Boira. That would be an appropriate description of pulsar. We are calling it a star because it is still shining and it is still not a dead body. If it becomes a white dwarf or a black hole, we would call that okay, the star is dead. Even with a supernova explosion or something like that, we would call that okay, it is no more a star. But this one, it is functioning. Yes.
And its mass মানে ভরটা তো সেমই থাকে না, এটা কোনোভাবে চেঞ্জ হয় না।
Yes. So let's say that the solar mass condensed in a very, very small space. So I was trying to figure out that how can I give you a comparison of the density. Like here we have a mountain range in Cape Town. So we generally compare it like that. If you take a teaspoon of this neutron star, most likely it will have a higher mass than the whole mountain range. But from Bangladesh perspective, I should say like if you take a spoon of neutron star, it's all the buildings in Dhaka or something like that should weigh kind of the same or more. It's highly dense. It's too heavy. But the property we care about here is the radio beam that goes through this magnetic axis or near the magnetic axis. So what happens is like where it used to spin around its own axis, right? And then it collapsed. So what will happen according to the conservation of angular momentum? As the mass concentrates in a very smaller place, the angular momentum will increase very, very fast, right? So let's say it used to rotate around its own axis, let's say in one day, like Earth. Now the whole Earth came to Gollamari, and it should spin very, very fast according to angular momentum conservation of angular momentum, right? That is why it spins so fast, like 1.3 seconds or 0.033 seconds, like the first example I gave. Anyway, so that is the primary understanding of pulsars or neutron stars. But we are not talking about neutron stars. Neutron stars is like pulsars, white dwarfs, and all other different kind of stars. All other things can be said as neutron stars. Pulsars is a special type of neutron star. Okay. Now we want to talk about the second part of my talk, which is gravitational waves, and I want to show you that how you can calculate theoretically what a gravitational wave is. So first, I want to show you the Maxwell's equations. I'm pausing this video here. Let's see. I wanted all these things to go before this thing. Okay. It seems like doesn't understand my. Anyway, so these are the four Maxwell's equations, and if we try to use the third and fourth equation together and use the first two into these two, we will get a wave equation like this one. Del square E equal to minus mu naught epsilon naught, second derivative of E with respect to time. And now, if we take all the parts in one side and keep the right hand side 0, you can see that it becomes a D'Alembert's operator, right? And the solution to that operator will be some sine or cos or exponential function, like any other sinusoids, any other wave equation. Now, what happens in our case? We have Einstein's general theory of relativity, Einstein's field equation, where R mu nu, G mu nu is the metric tensor, and T mu nu is the stress energy tensor, right? and G is the okay, I forgot what it's called. Now, what is G mu nu? G mu nu is the flat space-time matrix eta mu nu plus some perturbation. By perturbation, I mean that slight change. The change is very, very small. Let's say 0.00000001 or something like that. If I introduce this change to my flat space-time metric, what will happen to my field equation solution? So if I change my G mu nu or space-time metric, I can find out a new metric that will have 2 degrees of freedom. One is H plus, another one is H cross, and these are the 2 polarization modes of a gravitational wave. But the point is, we still don't know if it is a wave or not. So now you can see that this DLM version of H bar equal to 0 and the Maxwell's equations form are kind of the same. So from here we can, if we solve this equation, we will get something like this, and we can expand it to a sine and a cos wave. So now we know that okay, this space-time metric is actually behaving like a wave. So now we know that okay, when there is some massive objects collide and creates a vacuum, the wave should be like, the space-time should change according to this wave equation. Now, I want to show you that what this H plus and H cross polarization modes do. So here you can see that the H plus and H cross are evolving with time. So this ring of blue or red dots, what are they representing? They represent a unit circle of some mass distribution. Let's say all the masses are the same, and the gravitational wave is propagating from the screen to me. Okay, what will happen that mass, if you distribute a set of masses around a circle of a unit radius, it will change its distance like this, relative distance, I would say, like this. One changes only as a plus sign, and the other changes as a cross sign. So that's why the 2 names came from. Okay. Now, our final topic, which is what are PTA or pulsar timing array. So we assume that the sky is isotropic in terms of binary black holes, which means that if you look at any direction in the sky, you will encounter some binary black holes will be there, and they either collapsed or collapsing at the time of this observation. As in any direction, there is like many binary black holes. So we can assume that whenever in the past they collided, the wave is still propagating, because I'll show you why. The wavelength of this propagated wave will be in the scale of years. So we are good from that side. Now, if all this direction has some binary black holes and they collapse, whatever waves you are awaiting, these pulses are on the path of these waves, right? So when the pulse gives one pulse, either depending on the direction, either this pulse will arrive to Earth a few millisecond or microsecond before or after. As we already know that when the pulse should come, we can detect that is it coming before the time or after the time, and we want to calculate that extra time or that time difference. Now, why is that? I will tell you in the next few slides. But the point is, we will not do it for one pulsar, we will do it for multiple pulsars at the same time. Let's say we have, right now there is many groups, not many, but 5-6 groups in the world, they are working on the same project. And I think the maximum they have is 125 pulsars, all combined. So there is 125 pulsars, they are monitoring each second or each millisecond, I would say. They know precisely when the next pulses will come, and if they are delayed due to some background wave or not. That is our project basically. We need to detect if it is coming before or after the scheduled time. Now, what will we do with this knowledge that if it's coming before or coming after? So there is this famous theory from 1970s or 80s, which basically says that if you keep a track of all this time difference for a long time, then you can show that there is a correlation between any two pulsar pair, which basically means that, let's say you took two pulsars, A and B, and you want to calculate the correlation between them, and the correlation must be dependent on the angle between these two pulsars. So let's say you have two pulsars which is really close to each other, near 0 degree. So in that case, they will have the highest correlation. But if they are in a perpendicular direction or nearby, then they will have the anti-correlation. So they will correlate totally differently. Again, if they are like totally opposite direction, they will again be positively correlated, but not as much as if when they are in the same direction. So if you plot them, you will get this very nice plot that characterizes that if you have a gravitational wave in a signal or not. So we are trying to implement this thing for a long time. The group, they calculated data for like 15 years called nanograv. They will do the same thing in a very few time, I think with 20 years worth of data, where they kept track of all the millisecond pulsars and how they delayed with different time changes. Now, you might say that, okay, we know that in 2015, LIGO did it. What is the difference? The difference is in the frequency, or not the frequency, but the wavelength range. So when LIGO detected it, it was like the frequency was in hertz, 10 to 1,000 hertz, and it is coming from a single source. But when we are trying to do it, it is a stochastic wave, so that like in every direction of the sky, there is some wave generating binary black holes merging, right, or merged. So when all these waves come together, it becomes a stochastic wave. It becomes totally statistical. So you cannot just say that, okay, this comes from that one or this comes from that one. It's a combination of all these things. And now the frequency range changes. It goes to 10 to the power minus 9 to 10 to the power minus 7 hertz. That is the maximum. And if you convert it to the time, convert it to year, I think it goes few years, I think 10, 15 years worth of data. That's why people are observing this pulses for like so long. Okay. Now, the idea is that you need to time this pulses for a long time. But what do you mean by time? So when we say time, we mean that there is few obstacles when the signal leaves the pulsar and when the signal we receive on Earth. One of them we call is interstellar medium. In general, we know that the space between let's say the pulsar and Earth is empty, but it is not absolutely empty. And though it's emptier than most of our vacuums, so even if you create a vacuum in this Earth, the particle density inside that vacuum is still higher than the interstellar medium. But still, it is as the volume is so high, we encounter too many electrons on this line of sight of ours. So what happens is, like, when the particles interact, when the radio waves interact with these particles, depending on the frequency of the radio wave, it comes to Earth on different time. So we need to fix for them. And then there is other issues, like there is a lot of other variables that we need to take care of, like clock correction. What do we mean by clock correction? What we do is, let's say we observe a pulse on Earth now, but Earth itself is moving, right? So we cannot just take its position as a frame of reference, as a constant frame of reference. So what we do is we do a coordinate transformation, and we take the time from Earth's reference frame to the barycentric reference frame, because the barycenter is much more stable, constant reference frame than Earth. And then there is this DM that I just showed, that this frequency dependence, we need to correct for that. And there is this many other reason that can happen, due to which we get a certain delay. So we remove all the problems, and still there will be a certain deviation, which we conclude that deviation must come from this gravitational wave, and that will be very, very small. It will be in the order of microsecond, and then we take care of that thing. We keep that value in our dictionary or in our data, and we use that to detect the Helings and Downs curve. And there is a small list of parameters that we need to take care of. This is a list of few parameters for a certain pulsar. People work for a single pulsar, and then we create a list of pulsars that we want in our pulsar timing array, and then we keep observing those pulsars for like 10-15 years, and then we use those data to detect this Helings and Downs curve. So that is how we detect gravitational waves using pulsar timing array. Thank you. I hope it makes any sense. Questions? Sorry.
Yeah. Does anyone have any question?
Okay, I have one.
Yes.
So I don't remember, but did you show the relation between the angle and the correlation that you were talking about, and the
No,
intensity of the? Did you add the equation somewhere?
No, I didn't, but I can show you the equation. It's just a cosec theta.
Okay.
It's a very, very, very simple equation. So let me try to find it out.
So how do you define this theta? The
Theta is basically the observation angle between two pulsars from Earth. Nothing else.
So the observation angle from Earth. But
Yeah.
how does that affect the? Okay, so the intensity is basically how much we are observing it. It's not probably the actual intensity, or
Yes. You
Okay.
need to take care of all of this, but For our case, we are only considering the time when the pulse arrives at the barycenter.
Okay. Okay, and it's a cosec theta relationship. Okay.
It has a nice derivation. If you want, I can send you the proof. It's a shortcut proof, but there's too many details that I need to leave behind. I cannot read all this.
Yeah, yeah.
Stock parameters, there is this pulsar term, there is this earth term, and all those.
Okay.
Yeah.
Okay.
So what I could understand up till now, although many of the stuff flew over my head, PTA is like a mathematical array, right?
Mathematical? No.
Okay.
What do you mean by mathematical array?
Like, is it like a detector? Is it like a different detector than the other detector like LIGO, right?
So the thing is, here the pulsar is my detector.
Okay.
So I am looking for different pulsars across the sky, and I am looking for pulsars that I know fairly well, and it has timed in milliseconds, so that I can precisely go to the nanohertz range, right?
Yeah.
Let's say I found one here, I keep it. I found one here, I keep it. I found one here, I keep it. And let's say, like, in different direction, I have 50 pulsars. I keep all of them, and then I keep timing them when it should arrive, when it should arrive, and then I have a timing model that when it should come, right? In this timing model, I removed all the different noises I can understand. Like, there is red noise, which is basically frequency dependent noise. Due to different frequency ranges, it can come to Earth at different time. So I fix for that. And then there is one thing called Shapiro delay. So let's say this is a pulsar, but near this pulsar there's a black hole. So this pulsar is rotating a black hole, and whenever the signal comes across the black hole, due to the black hole's immense gravity, it comes even more late, right? So you need to correct for that first. Because from there is still no gravitational wave is coming. You're just getting the pulse signal, so you correct for that. And then there is this clock correction. So what will happen if I keep my time parameter from Earth? It will show a sinusoidal wave because Earth is rotating around the sun, right? If you consider the pulsar position fixed, then when the Earth is here, you get the signal slightly before time, and when the Earth is here, you get a certain delay. So it becomes a sinusoidal wave over time. So you want everything at the center of sun, or where the whole center of mass of the solar system is, which is basically the barycenter. So you coordinate transform the time to that place, if that makes any sense.
Yeah.
So now all these pulsars are my observatory, and I'm timing it all the time. And after that, I start calculating that what did I get, and did my data have this signature of waves inside it.
Okay. So I'm kind of trying to understand the experimental setup. So it's like an observation of those pulsars. So how does this observation is taking place? Like, is it like with microscope or
Radio telescopes, basically.
radio telescope? Okay.
So like in South Africa, they have this Meerkat radio telescope, so which observes, I think, 83 pulsars right now for this pulsar timing array observation. So what it does is like, so whenever the pulse, extra luminosity hits the antenna of our radio telescope disk, it takes the voltage as input. Okay, and you will see that small peak. And whenever a pulse from a certain pulsar comes and hits, it registers the characteristic pulse, and it gives the data that this is the time. This is the universal time when this pulsar hit my antenna, and when is the next one? When is the next one? And that becomes a data set for one pulsar.
Okay. Another question.
Yeah.
Like, what is the application of gravitational waves? Like, if we learn more about gravitational wave, we detect it and like much more on that. So what is the application of this other than, like increasing the academic syllabus?
In day-to-day life, nothing. But the thing is, we all are trying to find out the theory of everything, right?
Yeah.
So like our colleague, our next speaker will talk about string theory, and like also what I am working on, so you just saw that there's two polarization modes, right?
Mm-hmm.
That is according to Einstein's theory of gravity. But there is other theories, those we call modified theories of gravity. So if you consider them, you can get more polarization modes, maximum 6 till now according to literature. One of them is called scalar transverse mode, that I'm trying to detect that one in our data set. The idea is, if you can get any other polarization modes, that actually says that Einstein's theory is not the end of everything. There is more. There is some other theory that is talking behind the scene. And then the string theorists, they are talking about this for a long time. They can say that, okay, now we can come to scene because we are seeing some light that maybe our theory can provide a better result. So that kind of a passive solution, or it's not solution, but passively saying that string theory exists, maybe. So that could be one achievement theoretically, that you now know that which one is a better theory.
Well, condensed matter people can maybe like work on the devices.
Yeah, condensed matter people are also working on pulsars because they want to understand what is happening inside pulsar. So that is also an ongoing research topic, that we really don't know much about pulsar except the pulse, right? Whatever we calculated, it's basically based on their pulse profile, at which time they actually send at which time Earth get the pulsar signal. But the theory says that, okay, there is this core, there is this crust. So all these things, how the crust changes over time, how it affects the magnetic sphere, how it affects the magnetic field, all these things are like active research topic. Any questions outside
Like,
the talk?
it is like cheaper than LIGO, right? Because you are using the
Yes.
universe as a detector.
Yeah, it is. Yeah,
Yeah.
LIGO is kind of very expensive.
Also, you need like multiple stations.
Yes, I think LIGO has 2 stations, and now India is building one. I think there is somewhere else in the world there is another one. Maybe China, most likely. Yeah, LIGO is kind of expensive, and Americans find out all the newer ideas. So like now there is another proposal is going on, and I think in the next 5 to 10 years that will come to reality. It's called LISA. It is basically 3 radio telescopes on the sky. So it will rotate around the Earth and it will observe or take data from the orbit just to detect gravitational waves.
Bhai, I have a question.
Yes.
Uh, are we studying gravitational waves here, or the properties of pulsars exactly, or is it a mixture of both?
It's a mixture of both. Yeah. So we are using
And if
pulsars.
so,
Yeah.
yeah. And
We're
if so,
using
how does it correlate to the LIGO results? And is it just for verification, or is it like a completely different study?
it's a different study. It's a different study. Uh, what was the first question again? Difference between LIGO and this one, or?
No, the first question was, are we studying both or not? And how does the result correlate with the LIGO results?
We are
Are they
basically
similar
studying.
or are they
We are
different?
basically studying gravitational waves, but we are using pulsars as an instrument because we know that the timing is very, very precise. They considered kind of the most accurate cosmic clock. So you can get as precise as 10 to the minus 6 order of time. So whatever time you get it in, the error bar is very, very low. So if you want to get an error, it should be less than a microsecond. From that perspective, it is very, very accurate, and we can use it to detect gravitational waves. That is one. From the difference between LIGO and our method is basically, I think, twofold. One is what they did is they tried to detect the change in length of the two sides of the LIGO detector. One side must be shorter than the other when the gravitational wave passes through. Our one doesn't do anything. It just observes time and looks at the timing residual or the time difference between different pulsar pairs and tries to see that if you get the correlation and nothing else. So this is number one. And what did I try? And other thing is the frequency is very, very different. So for LIGO, it is like in seconds. So if you see the LIGO spike, it comes and stops like in between few milliseconds. It comes and goes, done. But here it's like the wavelength is like in years. So if you want to observe a part of the wave, the change in the wave, you have to wait for like 4 to 10 years to see a part of the wave, not the full wavelength. The wavelength must be in 20 years length. Yeah. And another reason for this experiment, I think, is the wavelength is so long that now you can understand that you can probe this as some other experiment for cosmic wave background and all those things. So you can probe it to even further and see the beginning of the universe and all those things. Yeah. I don't know much about it, so don't take my words for it.
Do the results from the pulsar experiment and LIGO, do they correlate? Like, are they similar? Do they lead to the same thing, or are they different?
So LIGO, of course, detected gravitational wave, right? They saw the sharp signal. We don't see such signals. We just see the correlation of these things. So both of our experiments saw these things, like the nanograv collaboration, they saw this back in 2023. But the problem is, to say that it's a detection, you need to come under a certain uncertainty range. They're still not there. So maybe in the next publication, they might achieve that one. So yeah. So both detect the gravitational wave if you want to know that. Yeah.
And bhai, what kind of pulsars are we looking at? Like, what's the range of frequencies?
We call it
Because
millisecond.
there are a lot of pulsars.
Yeah, we
Milliseconds.
call it millisecond pulsars. Basically, the pulsars that send us pulses in every millisecond range. That is what we're looking for. And if it is stable, yes, that is the guy.
And this method does not require the gravitational waves to pass through the Earth, right?
So it is always passing through the Earth. So that is the understanding. Because if you look at any direction, in every direction, either in today or in the past, there must be some binary black holes merged into each other. And when they merged, they sent us this immense amount of energy as a wave. So that thing is already there. So we don't need to consider that separately. So in any direction you look at, there is some binary black holes merged. They merge in different time scale, but the wave is propagating towards Earth, right? Yeah. There's a lot of them, infinite number of them. So that is why it's called stochastic gravitational wave background. It's not a single wave, it's a sum of all these waves.
Oh, I see. Okay, bhai, thank you.
Bhai, I had another question.
Yes.
So basically, it's too much for me. But then my main question was, are we using pulsar as an instrument or observatory to study the gravitational waves coming from the black hole, or we are using this to study the signals from the pulsar?
All of them. So first thing is we use our observatory, like a radio telescope, to observe the pulsars. And when they are sending signals to the telescope itself. And then we are using our calculations to see if there is this gravitational wave signature inside our data set, which basically says that we are using all the pulsars for our observations, or we are using the pulsars as our lab.
Okay, so as we are using the pulsars as our lab, so
Yeah.
can we measure another pulsar that is not sending us signals through a pulsar that is sending us signals? I mean, that's in a distance, but there's a medium in the pulsar.
I didn't understand the question actually, sorry.
What I said was, can we use a pulsar as a medium to measure another pulsar that is not sending us signals or any waves to our telescopes? But we know there is one, but
I don't think that is possible because radio waves is very difficult to detect. I don't know, maybe in the future they will come to that. Yeah, I don't know. I have no idea.
okay, that's all.
Okay,
Thank you.
so I have a question.
Yeah.
So there is noise, right? There must be some noise. So
Yeah.
how do they distinguish gravitational waves from those noises?
Yeah, great question. So there is a very, very vast research is going on only that topic. Like there is this solar wind, right? And when a signal is coming and there is solar wind, they must talk to each other and they must destroy each other's
Mhm.
signal, right? So
Mhm. Mhm.
whenever that thing happens, you can see it on the plots. And also we get data from NASA and other people who send rockets and all those things to, let's say, near solar orbit or something like that. So they get the, let's say, solar wind data first, and then we use the data and we try to see that at this time there is this much of solar wind existed on this region. So whatever pulses are coming from that side, what is happening to those signals at that time. So at the same time, when the solar wind is high, what is happening to our signal? Is it distorting? How much it is distorting? And can we model
Mhm.
that? And then we use that to other pulsars, right? So that is how people used to model all the different kind of noises. Like there's one called white noise or the telescope noise. So when
Okay.
a telescope receives a signal, there is some noise. I don't know what it's called, but there's some other noise. It's called, there's three different kind of white noises. And we used to subtract these noises from our signal, our pulsar signal. And then there's one that is called red noise signal, which is intrinsic to pulsar. So each pulsar has a different kind of red noise. So according to the pulsar, you need to calculate the red noise, and then it takes some time because it's frequency dependent, and you need to look at the pulsar over time, and then you remove the red noise. Uh, Basically, before removing, you need to model the red noise, that what will happen in the next, let's say, 4 years, and then you predict and you observe that how close your model is to the reality, and then you improve your model. It's basically kind of a machine learning, but no, we don't have that much data. And then once you understand that, okay, your model is good enough, you remove that kind of noises from your data, if that makes any sense.
Okay. Okay. I think I got some of it. Okay.
Sure, no problem.
If there are no other questions, we can end the session here.